we kind of identify on the periodic table. All of these are going to be named for the first element in the column. So if we're looking at the boron family, which is group 3A or group 13, so just like we made the observation yesterday, that the valence number of the element can be determined by the column that it's in. So group 3A is going to have 3 valence electrons. Now, in the boron family, it says it tends to make a +3 charge. Everything in that column, including boron, can be a +3 charge, even though boron is a metalloid. There are a couple of them that may have more than one charge, but +3 is the basis charge for it. So elements in that column are used for various things, from cleaning solutions to additives to glass to make it heat resistant, certain car parts, certain electrical components, aluminum for like pots and pans and cans and all of that. So the elements in there, for the most part, are really, really useful, especially boron, aluminum, and gallium are used in a lot of different things. I'm not so much sure on indium and thallium. I have to look up their specific uses. I'm not as familiar with those two elements. All right. And I give y'all a minute to make sure you get that.
That's like a normal whiteboard.
Hmm?
Is that like a normal whiteboard?
Mm-hmm. I can write with dry erase markers on there too. But when I do, if it gets dirty, it messes with this. Like it doesn't read it, track it correctly. Yeah, it's called an Epson bright screen or something like that. And you can see, like, whenever they were installing it, they scratched it and chipped it. So I want to take some like liquid paper or paint and paint that
They
one.
have like the whiteboard tape.
I'll have to look into that. I hadn't heard of that. But I hate it because sometimes on some of my questions, it just perfectly lines up and looks like a decimal point, and it shouldn't be. All right. The next group that we're going to look at is the carbon group. Carbon is a very, very, very important element for us because it is the element that drives organic chemistry. But carbon family group 4A or group 14 has 4 valence electrons. Now, let me kind of do this. So in the carbon family, GE, SN, and PB. So GE, SN, and PB will always make a +4, or can make a +4. SN and PB can also be a +2. So those elements under the stair-step line, the GE, the SN, and the PB can form positive ions. They tend to, their base charge is a +4, but they can also only give away 2 of their electrons and be a +2. They're kind of unique. And then carbon and silicone. typically only like to share their electrons. They don't like to form ions. But if they did form an ion, it would be the anions, the -4. All right. But carbon and silicon really don't ever form an ion. They're typically going to be found in covalent bonding only. So we don't really ever see that -4 charge, even though it is theoretically possible. All right. So this group is kind of the most diverse group on the periodic table. It has both nonmetals and metals and metalloids in it. And then the other thing that kind of makes it significant is on Earth, practically every life form that we have discovered on Earth is carbon-based, meaning the essential components of our structure and all of that have carbon in it. There are a couple of life forms. One of them is a single-celled organism called a diatom. A diatom is silicon-based. All right, that's actually whenever they die, the silicon shells on them actually form the sand that we get, and that's where a lot of that comes from. And then there's some archaeobacteria that are also silicon-based, very, very ancient bacterial cells. Or not ancient, they're still around. They're just very, very primitive bacteria cells. No nuclear membrane, all of this. It has all the components for life, but still a single-celled organism. All right. But everything else that we've discovered that's living on the planet is carbon-based. So organic chemistry is the largest branch of chemistry. A lot of people, if you talk to people that are in biology STEM majors like nursing or medical field, things like that, biochem, all of that, you're either going to find people that absolutely love organic or they absolutely hate it. The problem with organic chemistry, I like it, but you start dealing with carbon, hydrogen, oxygen a lot, and all of the compounds are carbon, hydrogen, oxygen, and something else, and it gets kind of difficult to distinguish one from the other. So that's what makes it hard. Some uses of elements in elements and compounds that come from carbon family: sugar, starch, gasoline, concrete, computers, radios, TVs, and pencils. Remember, the stuff that's in your pencil is not lead, it's graphite, it's carbon. All right, nitrogen family. Nitrogen family is group 5A, so it has 5 valence electrons. Nitrogen family, in general, we say it makes a -3 charge. That's because nitrogen, phosphorus, and arsenic, when they form ions, all tend to be -3. But when we look at antimony and bismuth, bless you again. Antimony and bismuth both are multivalent. They can make a +3, +5 charge. All right. Nitrogen makes up the major component of the air that we breathe, even though we don't technically use the nitrogen when we breathe it in. 78% of our atmosphere is nitrogen. Nitrogen is one of the key components in explosive compounds. TNT, toluene. trinitrotoluene. One of the key things, nitrogen is also a key ingredient in fertilizer, and so in the Marines. All right. Oxygen family, group 6A, has 6 valence electrons. Tends to have an oxidation number of -2 in charge. Oxygen is the second most abundant element in our atmosphere. It makes up about approximately 28 to 30% of the atmosphere, depending on where you look, what statistics you look at. So that leads me to another little soapbox of mine. A lot of the cars, when you buy a new car, you take it to the tire shop, they will offer to fill your tires with nitrogen. Gross. All right. So here's the thing. Nitrogen is already 78% of the atmosphere. So if you use an air compressor, you're mostly nitrogen in your tires anyway. They're trying to upcharge you for something. Don't buy into that. All right. Premium gas. There is a reason for that, but it's only for certain engines. If your engine doesn't tell you you need premium, don't use premium. It runs just as good on everything else. All right. So, oxygen family, we use oxygen for breathing, obviously. The sulfate compounds are big deals for fertilizer and plant foods. Oxygen in the form of ozone offers UV protection, as well as some of the other compounds that are in there are in certain medicines, gunpowder, coloring for glass, like stained glass and things like this. And just to test to see if anybody knows, what is the active ingredient in dandruff shampoo that so like Head and Shoulders and things like that? It's selenium. Se is the actual active ingredient that helps to prevent dandruff. So I found that out from one of the stupidest movies possible. It was science fiction, but they tried to make it sciencey. I think it's called. I think the actual name of the movie is Evolution, but it was like this asteroid hits and it's releasing these nitrogen-based organisms, and they kill them with selenium because if you look, selenium is to nitrogen as arsenic is to oxygen, kind of thing, stuff, or to carbon or something like that, and so that was the way because arsenic is poisonous to us, selenium was poisonous to them. I don't know. I have to look it up. All right. So the other major region, and they don't get individual group names. So we have this large block of elements right here in the center of the periodic table. And we call those the transition metals. Transition metals are also known as heavy metals. Typically these are the things that we associate as a metal. So it includes things like gold, silver, copper, nitrogen, nickel, zinc, iron, cobalt. Iron, nickel, and cobalt are the magnetic metals. So these are all the things that we kind of, when we think about a metal, it's one of those elements are the first ones that comes to mind. They tend to have a high density. And as far as reactivity, some of them are reactive, some of them are not. And their reactivity kind of varies depending on what they're interacting with. They like to bond with some things and don't like to bond with others. And so part of the reason why we call them transition is because it's hard to lock down a specific ionic charge or oxidation number for these. So all of these can have multiple ionic charges. And then I'll show you this. I'll show you this kind of as a, not as a demo, but just to kind of point it out. So, where did I set it? Set it back here. When we dissolve these metals from the transition group into solution, they tend to make colorful solutions. So this is a solution that is based on an iron ions, so it kind of makes that orange. Some of them will make like bright red, some of them will make pinks and all of that. This is a copper-based solution. Copper-based solutions tend to be blue, varying shades of blue. Aluminum kind of makes a greenish solution. I don't happen to have any aluminum solutions prepped right now. I want to say the solutions that I've seen with chromium tend to be kind of a grayish color, silverish gray in color when you look at them. So there's a lot of neat little things. Lead tends to make a darker gray solution, things like that. All right, and then the last little region area, and again, these are not families. They are actually part of the transition metals, but these two rows that get kind of separated out here. Remember, like I've told y'all before, that they actually belong right here, and it makes the periodic table spread out and look more like this. Really the only thing that they're kind of famous for is they contain the majority of the synthetic elements, the trans uranium elements, 93 and above. And then this whole row, starting at uranium, is radioactive. So every element past uranium is radioactive. All the time, like every version of it is radioactive.
So the ones in white?
All the ones that are outlined, all the synthetic elements, every one of them that we've created has been radioactive. Does that mean that there can't be a non-radioactive version of it? No, but we just haven't made one. And a lot of these elements are only still stable for a couple of seconds before they fall apart and decompose. All right. And then one more thing that I want to talk about with this one. I think I kind of mentioned this the other day. I'm not sure if I mentioned it in this class period or not. All right. So thinking about a nucleus of an atom, what are the two subatomic particles in the nucleus of the atom? Proton and neutron. So what does that make the overall charge of the nucleus? Positive. We made some statements at the beginning of this chapter that if I have everything that is the same charge, so if my nucleus is only positively charged, what should happen to the protons in there? What should they do to each other? Like charges push away, they repel. So if like charges repel, why doesn't a nucleus of an atom just fall apart? The electrons may have something to do with it, but think about it. Those electrons are on the outside. They're actually kind of free to leave if they choose. So if you look it up in a physics book, they're going to tell you strong nuclear force. But then when you try to look up what strong nuclear force is, they don't really give a good definition of it. I haven't found one that really says what it is. So what holds the nucleus together is a factor of a lot of things. Some part of it may be the electrons that are orbiting around it. Some of it might be the fact that the ratio between protons and neutrons, in a way, affect it to make it stable. It gives it just enough distance between the protons that they're not repelling. So if you think about it like you have two magnets and you try to push them together, before you have to get a certain closeness before you feel that force in between them. So those neutrons may fit in there. And that probably has something to do with why your lighter elements tend to be one proton for every one neutron, and then your heavier elements tend to be one proton for every like 1.5 neutrons or 2 neutrons. And then there's some other particles that they call gluons. They really don't know what they do, but they say they're sticky particles and hold them together. Just know that strong nuclear force is what we say holds them together. However, also know that we really don't know what holds them together. Now, that if any of you in your future endeavors decide to take the AP Chem test, you'll see this word Z effective charge come up. Z effective charge deals with the ratio to protons and electrons in there as to why some elements want to capture more electrons and bring them in, and some elements just want to lose their electrons. So that's it for the notes.